going through Chapter 2 of the engineering syllabus, the HSC syllabus, and, well, the Year 11 preliminary version of the engineering study syllabus, and I'm going to be looking at the materials component. I will be going through, so it's landscape products, chapter of the Copeland textbook. This is the previous edition, but I think it's pretty representative. So to start off, we're going to look at pistons. So pistons are not explicitly in the Year 11 syllabus. They are referred to as part of aeronautical engineering in the Year 12 syllabus, but it's worth mentioning that I will still test them because they can be considered part of the historical context of cars, which is what the part of the chapter we're looking at, and thus they're still testable in Year 11. To start off with, we're going to go to pistons here. That we talk about the four-stroke engine cycle. Now, just because there's four strokes, that doesn't mean there's literally four pistons. There usually are four pistons, but the idea is that each piston is doing a different thing at the same time. Now, the formal terms we use are intake, compression, combustion, and exhaust. They're the four steps. Sometimes we can call the combustion step, we can call that ignition, or we could call that the power stroke, because all the energy comes from this explosion. That orange light there, that's where all of the power comes from. But there are four terms that we often use, the simplified single syllable words, which is suck, squeeze, bang, blow. So let's have a quick look at that. We're not going to spend too long on this, but we can see here that in this case, this is a four-cylinder engine, but you can see that each one of those cylinders is doing a different stage of the process. Theoretically, it could work with less. It could work with two cylinders, but typically you want to have four. A V6 will have 6 cylinders, and so 2 of those cylinders will be doubled up, and more powerful cars will use V8 cylinders. I'll provide a link to this video on our school resources, but you probably shouldn't want to watch it independently and watch it in your or I'll show it to you in class. Now, a different kind of engine is a two-stroke engine. A two-stroke engine is much simpler. It has fewer moving parts, and it combines the 2 downstrokes and the 2 upstrokes. So the reason we use this in things like outboard motors, we use this in lawnmowers, we use this in cars, is that it's easier to repair. If it gets flooded, it's a lot easier to fix. It's lighter, but the reason why we don't use them all the time is because they're less efficient and they're more polluting. So they're going to cost you more money and they're going to be worse for the environment. So that's a two-stroke engine. This I wouldn't expect you to know too much about. I wouldn't necessarily expect you to be able to answer an exam question on two-stroke engines, but that doesn't mean it's not worthwhile knowing. And then we have diesel engines, and diesel engines work on the same principles as the four-stroke process. The difference is that they don't have spark plugs. So if you maybe watch this one here, I haven't watched these videos, so I can't say specifically. They don't have spark plugs, and spark plugs are what create that burst of energy, that power stroke. In the case of diesel engines, they just rely on compression because diesel ignites at a lower temperature. So it's just simply when the fuel is squirted into the chamber and then compressed, that compression, the heat and the compression is enough for the gas to spontaneously combust. So yeah, that's something to check out. There's also rotary engines, which is very interesting. A lot of people are interested in rotary engines, but not the focus of this course. I used to have a great video, Modern Marvels had a great video on engines, and I used to use that as a resource, but unfortunately they've taken that down and I don't have a recording of it, so I'll have to see what I can do to get that. But that was a really good hour-long, 40 minutes, something like that, documentary. Okay, so that's enough for me to cover engines for now. I'll say that those things really read the textbook, watch those 3 videos, and that should give you a pretty good understanding. In class, I actually have a plastic 4-stroke engine where you can see each of the strokes and you can see what's going on. But I think these videos do a really good job as well. Okay, so when my eldest daughter was very little, we took her to, with her grandfather, we took her to a museum in Wollongong where you can see an engine working, and he was a very hands-on kind of guy, and that's sort of part of the reason where I had got a better understanding of engines as well by looking at that model. Okay, so if you're ever in Wollongong, maybe worth checking out. Not a bad museum. Okay, so we're back to this picture. Everything is made of atoms. That's the start of the Feynman quote. All things are made of atoms, little particles. Yeah, you can read that if you want to read the Feynman lectures. Pretty good lectures from all accounts. I somehow managed to avoid ever doing physics at uni, so I don't have the same reverence or copy of the book. But okay, what we're going to look at is crystal structures. So we've looked earlier at BCC and FCC crystals. How far back will I have to go to find that? Will that be a pain? Okay, so we've learnt about crystals before, and we've learnt that atoms arrange themselves in crystals. We don't need that anymore. Atoms arrange themselves in crystals or a lattice. They stack, and they can stack in different ways. They can stack in an FCC or a simple cubic. They can stack themselves in a body-centered cubic, or an FCC is a face-centered cubic. And what we've also learnt about is we've learnt that there can be alloys of metals. So in a metal, what we'll have is we could have a pure metal. For example, we could have pure copper or pure gold, and they arrange themselves neatly in a lattice. Or we can have an alloy like steel, and steel is where we take a lot of iron atoms, and then we add in very small amounts of carbon. Do you remember what we call when we add a small amount in? It starts with the letter I. No, it's something. It ends in al. Into something. Interstitial alloys. Yeah. An interstitial alloy is where we squash a very small amount of a small atom into the lattice, and it doesn't mix up the lattice. We just squash a small amount in. We can also have substitutional alloys. That's can anyone give me an example of a substitutional alloy? Well, for example, we have brass. What are we substituting in brass? Yep, well, that's right. We have the main alloy. The main element is copper, and we're going to add small amounts of zinc. We're going to replace the copper with zinc. How much? Well, actually, not that small amount. We actually replace about 40% in brass. And stainless steel is both. Stainless steel, we replace some amount of iron, about 10%, with nickel or chromium, and we add about less than 1% carbon. These are both by weight, by the way, not by number of elements. Okay, so that gives us a good starting point. We also want to use the terms, so we call that a solid solution. So I've talked before about how in this case we have the solute and the solvent. The solvent is the thing that is the majority that's doing the dissolving. The solute is the thing that's being absorbed. So in the case of salt water, we would say that the water is the solvent and the salt is the solute. In the case of iron or steel, we'd say that the iron is the solvent and the carbon is the solute. We can also have precipitates. So if we keep adding enough salt until the point that we start to get solids forming at the bottom of the glass, we'd call that a precipitate. And we even have this, the main term we use precipitation is with clouds. Eventually the conditions get such that the air can no longer absorb any more water vapor. And when that happens, water will cease to form in the air. It will no longer be dissolved into the air. It will start to precipitate out. And when it precipitates out, it forms rain and starts to rain. We're going to learn about precipitation hardening later. When we do biomedical, we'll learn about stainless steel, and we'll learn about precipitation hardening. And then later in year 12, we'll learn about precipitation hardening of aluminium. But for the moment, I just want to put that word out there. Okay, so we've got a bit of a foundation of knowledge that we can start with. Now, what we're going to do is we're going to go back to the textbook, and we're going to skip all through the mechanics component because we're not really interested in that for this video. That stuff that, to be honest, is there is a video on couples that I have already made, and the rest of that stuff, it really kind of needs to be taught on a whiteboard most of the time. It's very hard to teach that in class. So during the pandemic year, that was one that I was glad we got to the point where I could teach that on a whiteboard. Okay, we're going to go to materials, and so we're going to talk about the modification of materials. Well, the main thing is that sometimes we want to make materials stronger. We want to increase the load that they can withstand, or we want to increase their resistance to indentation or scratching. So we either want to increase their strength, which is increasing the load, or more specifically the stress they can take before failure, or we want to increase their hardness so that they'll be more resistant to scratching or indentation. Well, how do we do that? Well, there's a couple of ways we can do that. One way is that we can, before we get to that. Okay, so often when we have these crystals that we talked about before, there's going to be little gaps in the crystals. Yeah, there are going to be little gaps that we can have as imperfections in those crystals. We call these dislocations. And what happens is they can slip. It's like if you've ever covered your textbooks or your workbooks with contact. Have you guys ever done that? And seen how you can get bubbles in the contact? And you know how you can move that bubble around the contact? Okay, well, so the same thing happens with metal crystals, that we can move that bubble around the crystal. Now, we can't really do this very well with ionic crystals because, do you remember when we talked about salt and ionic crystals? We talked about how they're in a very precarious balance. That if you push on any one side, then we'll have positive ions repelling other positive ions and negative ions repelling, and then that will throw off the whole balance of the crystal and it shatters. But metals, they can have irregularities in the crystal, and those irregularities or dislocations, they can be pushed around like a bubble in contact. Now, the idea is that the more bubbles there are, the more dislocations there are, well, ironically, it makes it harder to move around any one of those bubbles. So what we want to do is we want to look at what we want to do is we want to control the situation for these bubbles, how easy it is to move those bubbles around. So one option is that if we just hit the structure, if we take a lump of steel and we hit it, we just physically hammer it with a hammer. Or actually, a better example was if I go and get a metal coat hanger. I imagine you guys have seen this before, that if you bend a metal coat hanger, you can bend it back and forth. So sometimes you can bend it just a little bit and it will spring back. But if you bend it enough, it will hold its shape. So we know that steel has a limit to how far it can be stretched before it permanently changes shape. You guys familiar with this? Does that make sense? Intuitively? Yep. Okay. The next thing is, we know that when we bend those coat hangers back and forth and back and forth and back and forth, suddenly they break. Again, is that something you're familiar with? Yep. Okay, so we have that intuition. So there's an idea that the first time we bend it, we're actually making that steel stronger. And we're making it stronger because we're straightening out those bubbles, we're moving those bubbles away, or we'll get to later, what we're actually doing is we're making it harder for it to move those bubbles around. Let's just move that for the moment. Now, eventually, if we keep work hardening it enough, we'll get to the point where it's going to fail, right? We keep bending it back and forth, eventually the metal snaps. Now, how do we make it more difficult to move these bubbles? Well, the first thing is that we can just get to the point where there are no dislocations. We can just line up the crystals. Now, the thing is, it's also important to remember that these crystals, there's not just one giant crystal. If you have steel, there's not one giant crystal. If anything, there's going to be, well, I don't know what the order is. It's definitely going to be thousands, depends on how much there is, but there could be hundreds of thousands or billions of millions of crystals. These crystals are usually microscopic, but sometimes they're macroscopic. Macroscopic means they're big enough that you can see them with your eye. So an example of this is zinc. It makes really big crystals. So the next time you see galvanized steel, and I'll point out some galvanized steel to you, in B13 there's, if you look at the projector, underneath the projector is sitting on a galvanized steel tray. But You also see galvanized steel on, say, street signs that when you cross the road, when you press that button, that pole is probably going to be galvanized. And you can see those crystals with your eyes. They're really big crystals. They could be 5 millimeters across. Whereas steel is so small that the crystals really need to be seen under a microscope. So microscope, microscopic. Macro means they're big enough that you can see with your eyes. Still small, but big enough that you can see with your eyes. Okay, so the other thing we can do is if we hit steel, what we can do is we can actually break up those crystals. We can stretch the crystals. We can make those crystals, we can actually double the number of crystals by hitting it, by separating those crystals out, or by stretching or reordering the crystals. And the thing is, these bubbles that I talked about, these dislocations, they can't move from one crystal to another. So if we have more crystals, it's going to make it harder for us to move bubbles. So if we have more crystals, we're going to have a harder and stronger piece of steel. Okay, so that's the first way that we can make things stronger. Another way we can make things stronger is through heat treatment. Well, how do we make things stronger with heat treatment? What we can do is we can actually use heat to make smaller crystals, or the second option is that we can add in more interruptions into the metals. So when we talked over here about interstitial alloys, those interstitial alloys, so you see how we have the carbon, right? That little bit of carbon here, guys, that little bit of carbon here. A bubble or a dislocation won't move past one of these interstitial alloys. Yeah, the dislocation. So if you have a dislocation, this dislocation is kind of trapped between these interruptions in the lattice. And the more difficult it is for those dislocations to move, the stronger the metal is going to be. We good? Does that make sense? Okay. So once we have that concept, well, okay, what can we do? Well, there's 3 main heat treatment processes. So what we can do is we can change the carbon content. And if we have a carbon content, a higher carbon content, there's going to be more interstitial atoms. And the more interstitial atoms we have, the harder it is going to be for, if we have more interstitial alloys, the harder it's going to be for us to move those dislocations. I just want to see if I can find... Okay, so this is the picture I'm looking for. I don't know if you guys have seen this before when we saw the movie Austin Powers. So Austin Powers is a version of James Bond. It's a parody of James Bond. And the idea is that James Bond has had lots of reboots, which is why I use this picture. I guess I'll start here. So this video is again Real Engineering, and I have that open here. Real Engineering talks about heat treatment. This carries on from his previous one on material properties. You probably want to watch the materials property one before you watch the heat treatment one. And the idea is that I look at it as, well, if we had 3 different reboots. So we have Roger Moore was a reboot of James Bond. And we had Pierce Brosnan. He was another reboot of James Bond. And then we had Daniel Craig, who was yet another reboot. I think there's been 7 reboots, but I'm focusing on the big ones. So originally there was Sean Connery, then Roger Moore was the first reboot. For me, for people of my generation, this is Pierce Brosnan was the big reboot of my generation, and then the current reboot, the longest serving Bond is Daniel Craig. I think he's the only Bond to have made a movie across 3 decades. So I guess the 2020s, the 2010s, and the 2000s. Okay, so before I get onto that, let's talk about carbon contents. So I have kind of moved on from the Bond analogy because a lot of people don't know who Bond is. Have you guys ever really watched a Bond movie? No, only have watched Austin Powers. Austin Powers, I don't know. Funny, does it hold up? Yeah. So it's a kind of an iffy. A lot of students I have said that they thought it was still funny enough. But I remember my kids were not super fans. Okay. Pretty lukewarm on it. Okay. So the idea is, well, first of all, we want to understand the composition of the composition of different amounts of carbon. So when we talk about steel, we're going to refer to it by its carbon content. So if I go here, in this video, the real engineering guy, he starts with what we call the iron-carbon phase diagram. So iron and carbon, if we put them together, we call that steel. And there's different phases or different formations. Remember we talked about crystals that could be in different kinds of structures. We called them polymorphous. Yeah, and we said steel was a polymorphous material. It exists in different kinds of different structures. Well, at a certain temperature, over 16, well, if we get to 2000 degrees, it doesn't matter how much iron or how much carbon you have, you're going to get liquid, right, over 2000 degrees. As the temperature drops, well, whether or not it becomes solid depends a lot on the composition. If we're at about this 4 degree point, right, the 4 degree point, what did we say? If it's over 2 degrees, between 2 and 4 degrees, what do we call that? Starts with a C. It's two words starting with C. Something iron. Cast iron. And so it makes sense that metals that we want to cast will have lower melting points. So we can see that there's a lower melting point in that 2 to 4 temperatures range. After 6%, we call that pig iron, and I've only mentioned that very briefly. That pig iron is kind of rubbish, and I probably have mentioned my story about Pig Iron Bob and the song about pig iron, but that's rubbish. It's not an engineering material. It's a waste product, and we don't want to use it. Okay. But as the guy on this engineering video says, that we don't really care about this whole diagram. This whole diagram, too confusing. Let's zoom in, right? And we're going to zoom in to this diagram. And that's exactly what we're going to do. So what I've got here is I've got a picture of Austin Powers, and behind him is a whole bunch of ducks. The reason why I've got this picture of Austin Powers is because the steel, the version of steel I'm going to talk about first is called austenite, or gamma steel. Gamma being the Greek letter for G, the fourth letter of the alphabet. Third letter of the alphabet. I take that back. Okay, so let's go back. Okay, so we've got austenite, and I wanted you. The reason why he was standing behind all those ducks is because I wanted you to remember that austenite is ductile. It means it's very easy to move. Now that makes sense because it's so hot. And I always, when I do this in class, I like to touch the whiteboard and touch austenite. So hot, you know, like, because he's so good looking. He has all these people chasing after him. He's so good looking, yeah. Which I don't know how I didn't get this song ready to go, but we have the austenite theme song. Okay, and the idea is that at high temperatures we're going to get this. This is the Greek letter gamma. We're going to get austenite, and Austin Powers. He's pretty hot, right? And so he's so hot that he's got a lot of people chasing after him, and when people spot him, they very excited because he's so hot, right? Austenite doesn't exist in room temperature. Austenite only exists over 700 degrees at minimum. Okay, as fun as to leave that in the background, austenite is a face-centered cubic. That means that the crystal is arranged like this. See how they're chasing after him because he's so hot? Austenite is face-centered cubic and only exists at high temperature. It's ductile. That's why he's standing in front of all the ducks. Okay, so austenite is a face-centered cubic. How do I remember that? Well, I make sure... How do I remember that? Well, look at his face. Austin Powers, he doesn't have a great face. He has to. He gets his teeth done at the end of the movie, and he has terrible teeth, and that's because Austin Powers doesn't have a great face. It's funny, I couldn't actually get a photo before where he has his bad teeth, so I had to Photoshop to make his teeth look a little bit worse. But the whole point is, I want you to remember, Austin Powers doesn't have a great face. He's all about the face, though, right? Austin Powers standing in front of the ducks. Standing in front of the ducks because he's ductile. Austin, heat, face. Face-centered cubic. Okay. Then, what we also have is we have another allotrope of carbon. We have another form of carbon, which is body-centered cubic. Again, the Real Engineering video, he talks about this here, where he compares the two different crystal structures. And he talks about the slip planes of the different crystal structures. A little bit beyond the scope of this course. Not everything he's talking about is in the course here. So he talks about body-centered cubic, and then he compares it to face-centered cubic. And he talks about why having the combination of those two is so important. And we're going to get to where we see a combination of those two. Anyway, what happens is that at low temperatures we get this thing called ferrite, and ferrite is a body-centered cubic, and it's BCT. BCC.